Hey guys, we're back. All right, so we are going to click 1A, go to our notes. I'm there. We stopped last time right after learning about what an Euler circuit is and what an Euler path is. Okay, let's take a look at Euler's theorems. These are going to help us out. These are going to make things a little easier for us. So theorem 1, if a graph is connected and every vertex is even, got an Euler circuit. Now, if a graph has any odd vertices at all, no Euler circuit. Let's take a look. Here, 2, 4, 2, and 4. So all of your vertices are of even degree. They're all even. So an Euler circuit does exist. Let's see if we can find it. I'm going to grab red, make it a little smaller. All right. So 1, 2, 3, 4, 5, 6. We did it. All right, what about this one? 2, 4, 4, 4, 4, 2. Yeah, it should work here too. I'll start here. Oh, wait a minute. Didn't we do this at the beginning of the unit? Yep, this is the one, and you'll see that it ends us up right back where we started. Excellent work. Now here, I have 2 odd vertices, so there's no Euler circuit. But what about a path? Yeah, I can do an Euler path, so I'll still cover every edge, but I won't end up back where I started. And the same here, I have 1, 2 odd vertices. I'll start at this one. So there's no Euler circuit, but I should be able to cover all the edges with an Euler path. There we go. So what does that tell us about Euler paths? Well, it tells us that if we have exactly 2 odd vertices, exactly 2, then we have an Euler path. So here you have your odd vertex here and your odd vertex here, exactly 2. And any such path must start and end on the odd vertices. Did you notice that's what I did up here? I started at 3, I ended at 3, and here I started at 1 and ended at 1. So here, do I have any Euler circuits? No. I have odd vertices. No Euler circuit exists. However, there is an Euler path because there's exactly 2 odd vertices. Let's look. I'll start at this one, B, which means I'm going to have to end at C. So I'll go down, I'll loop up and around from A back to B, maybe to E, and then D, and then C, and then back to E, and then to A, and finally down to C. And we did it. All right. So, is there an Euler circuit or path here? Here we have A, which is degree 2, 2 edges connect. B is degree 2, 2 edges connect. C, 1, 2, 3, 4, 5. No Euler circuit because I've got an odd vertex. F is degree 2, D is degree 2, E is degree 3. I have 2 odd vertices, so yes, I can have an Euler path. Let's find it. Now, the one I do isn't going to be the only one available, but I'm going to start here at C, and I'm going to go C, A, B, back to C, because I can go through a vertex more than once, just not an edge. So again, C, A, B, C, F, E, D, C, E. Started at C, which is an odd vertex, ended at E, which is an odd vertex. All right, and our last Euler theorem is that the sum of the degrees of all the vertices in a graph is twice the number of edges. And a graph must always have an even number of odd vertices. Okay, let's take a look. So if I have a graph with order 6 and the sum of all the degrees is 18, does the graph have an Euler circuit or path? All right, well, if I have 6 vertices and the sum of the degrees is 18, to get the number of edges, I divide that by 2. So 18 divided by 2 is 9. And when I created that here, I have a connected graph with 6 vertices and 9 sides. The one I drew has a degree 2, degree 3, degree 1, 2, 3, 4, degree 2, degree 3, 1, 2, degree 4. So there's no Euler circuits because there's odd vertices. But I only have 2. C and E are my odd vertices. So yes, there's an Euler path because there's exactly 2 odd vertices. So to make this a little easier, we have something called Flurrys algorithm, which is what we use when we're looking for an Euler circuit or an Euler path. So when you're using Flurrys algorithm, bridges are the last edges you want to travel. Only do it if you literally have no other option. So number 1, you make sure that either a circuit or path is possible by checking the degrees of the vertices. If a circuit exists, you can start anywhere you want. You can make it happen. But if a path exists, but not a circuit, you must start at one of the 2 odd vertices. So you travel through an edge if and only if it is not a bridge to an untraveled part, or there is no alternative. So you can label the edges in order as you travel on your copy. So here, finding an Euler path, I'm going to get my pen here. All right. So if I find the degrees A, 1, 2, 3, 4, B is 2, C is 4, D is 4, E is 2, and F is 4, which means I've got an Euler circuit. All my vertices are of even degree. Now, in this case, I started at A, but you could literally start anywhere. And I went here and I labeled that 1. I must travel here. I'm going to travel to D, and then to E, and then F, and then I'll go back to D, and then to A, and then to C, and then to F, and then I finish back at A. Now, there were no bridges here, but remember, if you have bridges to a different portion of the graph, travel them last, unless you have no other option. All right, so we are now at our stopping point. We're going to click over to our discrete math cover sheet and go to practice set 3. And here you're going to use Flurrys algorithm to find an Euler circuit. Same here. I think you're going to use it to find an Euler path here. All right. Good luck.